5.4, the central limit theorem. Now that we know a good bit about how normal distributions work, let's see what that has to do with the central limit theorem. For starters, we want to know a little bit about what we mean by a distribution of sample means. And there's kind of a lot going on in that definition. It seems to me that the best way to understand it fully is to run through a little bit of an example. We're going to see what it means to look at the means computed from all possible random samples with replacement of a specific size. So to kind of break that down and see what it means, let's say we started with a very small little population. Maybe this is the amount of money 4 friends spent on their textbooks one semester. So for that population, I've put it into my calculator and found that the mean or the average amount spent by these friends is $165. And the standard deviation is 38.4. We want to then start thinking about taking every possible random sample of a certain size from this population. So the example here suggests that we start with samples of 2. From that population, if I picked 2 of the 4 items and replacement is allowed, I could pick that 120 for the first and the second choice. Or maybe I pick the 120 first and then the 140 next. Or maybe the 120 first and the 180 next. If we're a little bit systematic about this, we may be able to find all of the possible samples of size 2 without missing any or duplicating any. So I've already paired 120 up with itself and 140 and 180. I still need to pair it up with 220. Seems like I'm going to have 4 choices for that first item and 4 choices for that second item, so anticipating 4 times 4 or 16 possible samples of size 2. You might pause the video for a second and see if you can find the 4 that start with 140, the 4 that start with 180, and the 4 that start with 220. We'll end up pairing 140 with all 4 of the items, so 140 and 120, 140 and 140, 140 and 180, 140 and 220, and the same for the 180. It will get paired with all 4 of the numbers in the population. And lastly, we need to pair the 220 with all 4 of the numbers in the population. Oops. So what we've done so far is taken all possible random samples of size 2 from our population. And it says then what we want to do is look at the means of all of these samples. So I want to know what the mean of 120 and 120 is. If I add them together and divide by 2, I'll get 120. And we want to know what the mean of 120 and 140 is. If I add them together and divide by 2, I'll get 130. The mean for 120 and 180 is 150. The mean for 220 and 120 is 170. Maybe you'd pause the video again and see if you could average each of these pairs. We want to find all 16 sample means. If you got 130, 140, 160, and 180 for the next 4, you're off to a great start. And 150, 160, 180, and 200 for the next 4. Then the last 4 would be 170, 180, 200, and 220. So the distribution of sample means, distribution means we've got a complete list of all of the sample means when we took samples of 2 from this population. Something we might want to do is we might want to find the overall mean for all of those sample means. In other words, add all 16 of these together and see what the average is. I've done it on the calculator here. I got 165. And then again, for this new set of 16 numbers, we might want to find the standard deviation. And I've done this here also. I got 27.2. So what we'd like to do is kind of go back and compare with the mean of the original population. So the mean of all of these sample means is 165, and it turns out that's the same as it was for the original population. And that might kind of make sense if we have every possible sample of size 2, the middle of that should be right where the middle of the original data set was. On the other hand, the standard deviation changed a little bit. It went from 38.4 down to 27.2. And we actually are going to see on the next page that they're related an exact way. We found that this mean equals that mean. They're exactly the same. But this standard deviation is not exactly that standard deviation. But if I took the original one and divided by the square root of n, that would come out the same. In other words, let's go back to that 38.4 and let's divide it by the square root of n, the square root of 2 in this case. And that does give us this exact same number, 27.2. So we have a couple of properties that result from what we've seen here from our distribution of sample means. Turns out that the mean of all the sample means, that's the symbol mu sub x bar, the overall mean of all the sample means equals the original population mean, mu. And the standard deviation of all the sample means, sometimes called standard error, is smaller than the standard deviation of the population because it's the standard deviation of the population divided by the square root of n. So when we're dealing with sample means, that change will be reflected a little bit in our z-score formula, where we used to have x minus mu. Because we're now looking at sample means, we'll have an x bar instead of an x bar minus mu. And where it used to just be divided by sigma, because now we see that that standard error or standard deviation of the sample mean changed a little bit, we want to have sigma divided by the square root of n. So when we're dealing with a distribution of sample means, we want to treat our z-score a little bit differently. So as a result of all this, when we're looking at a distribution of sample means, as the sample size increases, we're going to find that we have a normal distribution, which means we can use all the tricks we've been learning lately here in Chapter 5 on problems related to a distribution of sample means. Here's a little bit of an example from that same population we had on the first page. If I took samples of 1, the distribution looks like this, maybe kind of skewed to the right. And when I go to samples of 2, like our 16 sample means, the distribution becomes closer to symmetric. You might still say it's a little bit skewed to the right, but it's definitely more symmetric than that one was. And that's what we know from the central limit theorem. One kind of question we'll see in the homework is going to ask us to use the ideas we saw here in number 1 and number 2. Just see that the means are equal and see what effect the standard deviation has had. An example of that is here on the next page. It says the heights of mature trees of a specific species are normally distributed with a mean of 61 feet and a standard deviation of 7.25 feet. So they're telling us the overall mean mu is 61 and the overall standard deviation sigma is 7.25. We know from what we saw on the previous page that the mean of the sampling distribution, mu sub x bar, equals the original mean. So we know that mu sub x bar in this case will be 61. And we know that the standard deviation of the sampling distribution, which you see is also called standard error, is going to be the original standard deviation divided by the square root of n. So we want to take 7.25 and we want to divide it by the square root of samples of 14, square root of 14. So n in this problem was 14. So 7.25 divided by square root 14. And StatLab will let us know how to round. Looks like something like 1.94, 1.9, depending how you would round it for the standard error. Those same homework problems will then ask us to sketch a graph of the sampling distribution. So keep in mind what we know, that the mean is going to be in the middle, the mean of the sampling distribution. And remember what we know about standard deviation and normal distributions. We know there should be 3 standard deviations to take you to pretty much the top of the curve, and 3 standard deviations to take you pretty much to the bottom of the curve. So imagine if we added 1.94 on 3 times, 61 plus 3 of these 1.94s. That would put the end of the curve being pretty much 66.82. So I'm not saying we could come up with this number exactly, but we know it's a decent scale. This question would be multiple choice on our homework, so be sure to look for one where that mean of the sampling distribution is in the middle, and where it would take about 3 of your standard errors to get out to the end. So just some tips to help you know how to pick the right one.